Okay, welcome back Physics 20s to our next lesson in Chapter 1. This is 1.3, and today we're going to be talking about uniform motion. Okay, so to begin this lesson, we're going to talk about what motion is. Now, it's probably a pretty familiar word, and then it means that something is moving, but how do we quantify something as moving? Well, movement is really a rate of how much distance is covered or how much position is changed in a certain amount of time. We have two ways of describing this. Our first one is with speed. And speed is going to be a measure of how much distance you cover and how much time it takes to cover that. Now these are inversely proportional. We can see S is equal to D divided by T. And let's take a look at why it's set up that way. So if we have a person and they're going to be moving, the distance that they move is going to represent the value D in that formula. And the time is going to be how long it took to cover that distance. Okay, now let's look at the relationship between time and speed first. If I'm going to cover that same distance, so the top number stays the same, but I'm going to decrease my value for time, that means that I move faster. I travel that same distance in a shorter time. We'll describe that as a higher speed or going faster. So the person moves faster as they covered it in less time. Similarly, if we have the same amount of time, say 1 second, and we travel a further distance, so I increase my distance, my speed will go up if I do it in the same amount of time. So increasing distance or decreasing time are going to make it so we're going faster if the other variable is the same. The other way that we describe motion is velocity, and it looks pretty similar. It's v is equal to d over t, so it looks pretty similar. It's just that d is now representing displacement instead of distance. We did look at the difference between distance and displacement in previous lessons, and a reminder that distance is a scalar quantity, just talking about how far you've gone, and displacement is a vector, saying in what direction and how far did we end up from where we started. So this means that speed is also going to be a scalar. We're just worried about how fast, whereas then velocity is a vector. We're worried about how fast, but also in which direction. So looking at this person, if we're going to consider their velocity, we might just say which way is forwards and backwards. And if they move this direction, and I say that's moving forwards, I would assign a plus to this direction, to the right, and a negative to the left. So this way would be a positive velocity. If it turns around and runs the other way, that would be a negative velocity. Now, for pretty much the entire course, we're going to have to consider if the motion is going forwards or backwards or what direction it's in. So we're going to use pretty much exclusively velocity, so you can get used to using v is equal to d over t. And before we leave this slide, I have motion at the top, but the title of this video is uniform motion. What does uniform motion mean? Well, uniform means consistent or not changing. So we apply that to non-changing motion, and we're talking about velocity. That means how fast we're going and the direction is going to stay consistent, not changing. So if a car is driving at 100 kilometers per hour north and stays at that speed and stays at that direction, that's considered uniform motion. If there's any speeding up, slowing down, or changing direction, that's now going to be considered accelerated motion, and that's what we'll look at in the next video. So let's take all that information and now put it into some notes that you can write down for studying. First, motion is described as either speed or velocity and as a rate of how fast you change your position or distance over time. We can see the formula here for speed is distance over time, or S is equal to d over t. This is a scalar quantity, just worried about the value, not the direction. Didn't mention this before, but it's good to have in your notes the units for motion. It's going to be in meters per second or kilometers per hour most frequently, and that comes from the formula. The d, or the distance, is going to be measured in usually meters or kilometers, divided by the time, which is a unit of seconds or hours, again, most commonly. For velocity, again, similar formula, displacement over time, v is equal to d over t. I threw some other symbols in here. There's an arrow over top of the v and the d. That's to indicate that these are vectors. It's good to know that it looks that way most formally, but you don't need to write those in on a worksheet or a test. You'd be okay just to write v is equal to d over t. And again, that triangle d means displacement. Good reminder that this is a vector quantity, so we're considering direction, even if it's just plus or minus, or north, south, east, or west. And the units, again, the same, meters per second or kilometers per hour. Last part to throw in, uniform motion. That uniform motion saying that we are moving at a constant velocity or not changing velocity. We're not changing how fast we're going, we're not changing the direction. Okay, now that we know what motion and velocity is, we're going to talk about simultaneous velocities, which means when two motions are occurring at the same time. Common examples of this are maybe when a boat is driving on the water and the water is also moving, or a plane is flying in the air and the air is also moving. Multiple velocities are occurring at the same time. How we're going to figure out the overall motion is very similar to when we were adding different distances and looking at vector arrows. The main difference is that when we're looking at velocity, the object is going to follow the resulting vector, not the individual components. It's hard to make sense of with words, so let's take a look at some examples to see the difference. Okay, so here we're going to use two similar examples. On the left, I'm going to use displacement, and on the right, we're going to talk about velocity. On the left for displacement, let's say that a person walks north 5 meters and then walks south 2 meters, or if we're just using plus and minus, +5, then -2. The resulting vector would be from the start of the first to the end of the last, and we get a value of +3 meters or 3 meters north. The person walks forwards, then walks backwards. That's what the motion looked like. And again, we get a displacement of +3 meters. Velocity, let's use even some similar numbers. Let's say that the boat is driving at 5 meters per second on the water, upwards or north. We'll put a positive value to that. But then the river is now flowing in the opposite direction, going 2 meters per second downwards, or -2 meters per second. I have a very similar diagram, and the result is 3 meters per second upwards. The only difference really here is that the boat isn't going to go up and down, it's going to travel just more slowly forwards. So the velocity is going forwards at 3 meters per second, which would look like this, going at that rate forwards the whole time. Let's now compare what if there's two dimensions, so a vertical and a horizontal component. Again, displacement on the left, velocity on the right. If a person walks forwards 4 meters, let's say that's north, and then east 3 meters, their displacement would be 5 meters from where they began at an angled northeast angle. So the person's going to walk up on the red, across on the yellow, and they end up 5 meters from where they started. We would write their displacement as 5 meters. Because this is a vector, we'd have to include details on their direction. It'd be 37 degrees east of north by using tan with our other components. Now to the right side for a very similar diagram, let's say the boat's driving at 4 meters per second north, but now the river that they're on is flowing at 3 meters per second east. We're going to have a very similar diagram that they're going to be moving at a total velocity of 5 meters per second. They're going to be moving at an angle. So velocity is 5 meters per second, and the boat's going to travel along that black line, not along the red and the yellow. So the boat's motion from someone viewing it from above would look like this. We can describe that as 5 meters per second, again in the angle of 37 degrees east of north. So hopefully those diagrams hope to show the difference between adding those vectors for displacement and velocity. Let's put some of those things in the notes here. What we did for the velocity vectors is we added them head to tail, and then we drew our resulting vector from the tail of the first to the head of the last. That was that black line. And then the really big difference between the two was the object for velocity moves along that resulting vector line, doesn't follow the separate components. Now to conclude this video, I want to look at some of the most challenging questions where you have to add velocity vectors. And this is when you have to add two vectors that are at an angle. It's kind of similar to what we did with displacement. We have the same steps here of where if you have angled vectors, your first step is to break them into their x and y parts. So you have an angled vector, break it into its horizontal and vertical components. Once you have all the horizontal and vertical components, add those up together. The verticals with the verticals, horizontals with the horizontals. You can do this in a diagram or an x and y chart, and we're going to do an example here which shows kind of using both to figure out the overall resulting velocity. Okay, so this would be considered a pretty challenging question in our course. Let's say that the boat is traveling at an angle and the river is also traveling at an angle, and we want to figure out the overall velocity of the boat. Okay, the boat's traveling at 6 meters per second relative to the water, and the water is traveling at 3 meters per second. The river is at an angle of 20 degrees above the horizontal, and the boat's going at 30 degrees relative to the vertical. So how we're going to figure out the overall velocity is we're first going to add the vectors head to tail. I'm going to slide the blue vector up here, and then I'm going to draw my resulting vector from the tail of the first to the head of the second. That red line represents the overall velocity of the boat. Now we don't really have a nice triangle here. It's not a right angle triangle. So I can't really find out too much from that diagram. So to get a better diagram and figure out more information, I'm going to break the yellow and blue arrows into their x and y components. So I draw a right angle triangle, use cosine to find my vertical component, and sine to find my horizontal component. Do the same for the blue vector, find my vertical, and find my horizontal component. Now that I know those, I could put this in a diagram altogether, and we'll get to that in a second, but first I'm going to use an X and Y chart, as that works well for most students. So let's kind of blur out the background here and create an X and Y chart. I'm going to put my vertical components over here in Y, and my horizontal here in X. Again, here putting the horizontal in X and the vertical in Y. Next, I'm going to add these up. The 3 plus the 2.819 gives me a total of 5.819 in the X direction, or to the right. And then the Y direction, I have a total of 6.22 up. Now I can show on a diagram where those numbers go. I make a triangle based off that red resulting vector. Then I use Pythagorean theorem to find the value of the hypotenuse. 8.5 meters per second is how fast the boat is going along that line, and it's traveling at an angle of 47 degrees north of east. So I hope that helped you to understand what motion is and also how to add velocity vectors. Thank you so much for watching this video, and I will see you in the next one.